All right, let's dive right into this explainer. Today, we're taking a simulated first-person flight straight into the ultimate cosmic abyss, a supermassive black hole. We're going to explore what it actually looks and feels like to cross the ultimate boundary in the universe. We'll be pulling entirely from astrophysics data, NASA supercomputer visualizations, and general relativity to see exactly what happens when the laws of physics are pushed to their absolute breaking point. Buckle up.
You know, we often picture black holes like that awe-inspiring one in the movie Interstellar. But as Sarah Issoun from the Event Horizon Telescope team points out, people constantly ask why actual images of black holes just don't match up with Hollywood's vision. So what does astrophysics tell us it actually looks like to fall into one?
Section 1. Hollywood versus Astrophysical Reality.
Okay, so while the Interstellar team did consult physicists, most notably Nobel Prize winner Kip Thorne, they definitely tweaked the visuals for drama. On the one hand, you have the movie's version, this razor-thin, perfectly symmetric, beautifully bright disk. But reality? It's way more chaotic. The movie producers actually switched off the Doppler effect just to make it look prettier. In reality, a black hole's accretion disk is much thicker. Think of it more like a massive glowing donut. And because it's spinning incredibly fast, that Doppler effect makes the approaching side intensely bluish-white and scorching hot, while the receding side looks way dimmer and redder.
Section 2. Anatomy of a black hole. The absolutely crucial landmark on our journey is the event horizon. This is it, the literal point of no return. It's this mathematical boundary where the gravitational pull gets so staggeringly intense that to escape it, you'd have to travel faster than the speed of light. And since nothing can do that, whatever heavily compressed stuff is sitting at the center is forever hidden from us behind this pitch-dark sphere. As we get closer, the visual chaos really starts to unfold in these distinct layers. First, you'll notice the accretion disk, that swirling, superheated gas we talked about. Piercing right through that are the photon rings. These are crazy thin, glowing bands of light that are just trapped in an endless orbit. Surrounding the whole shebang is the Einstein ring, which acts like this massive cosmic funhouse mirror, warping and literally inverting the entire universe behind the black hole. And in the very center, the shadow. It's a dark inner void that actually looks twice as big as the event horizon itself just because of how violently it bends the light around it. Section 3. The supercomputer simulation. For our simulated plunge, we're targeting a supermassive black hole that's about 4.3 million times the mass of our sun. And that's not just a random number. It perfectly matches the size of the monster lurking right at the center of our very own Milky Way galaxy. Now, fun fact, if you're going to fall into a black hole, you actually want it to be a supermassive one. Smaller, stellar mass black holes have such extreme tidal forces right at their edges that they'd rip you apart long before you even reach the event horizon. Yikes. NASA astrophysicist Jeremy Schmidtman and scientist Brian Powell are the brains behind this stunning simulation. As Schmidtman explains, the whole goal here was to take the incredibly abstract, frankly mind-bending math of Einstein's general relativity and turn it into a visceral, visual consequence. Basically, they transformed incredibly complex math into a reality that you and I can actually sit back and witness. Generating this virtual trip took some staggering computing power, churning out 10 terabytes of data. To put that massive number into perspective, that is equal to roughly half of the estimated text content held in the entire Library of Congress, just for one simulation. And this really brilliantly illustrates the sheer horsepower of NASA's Discover supercomputer. The visualization ran for 5 days straight, but get this. It used a mere 0.3% of the supercomputer's 129,000 processors. If you tried to render this exact same mathematical journey on your everyday laptop, it would take you more than a decade to finish. Section 4. Plunging toward the horizon. All right, we start our descent from a totally safe distance of 400 million miles out. Over the course of 3 hours in real time, we plummet inward, completing 2 full 30-minute orbits along the way. Now, as we accelerate closer and closer to the speed of light, the glow from the accretion disk and the background stars seriously amplifies. The light actually shifts toward a blinding white right in our direction of travel. It's kind of like how the sound of an oncoming race car gets higher pitched as it speeds towards you, except here we're seeing it happen with the frequency of light. Now, check out this totally wild contrast in perspective. As the one actually falling in, you experience this as a rapid 3-hour plunge straight toward the event horizon. But if a friend were watching you from a mothership safely far away, they'd never actually see you cross it.
Because gravity warps space-time so severely, your friend would just see your image slow down, get heavily distorted, and completely freeze right at the edge of the horizon, slowly fading to red. This bizarre optical illusion is exactly why astronomers originally called black holes frozen stars. Section 5. The point of no return. So what happens when we finally cross? Based on mathematical maps of space-time called Kruskal manifold models, crossing the horizon doesn't look like smashing into a physical wall. The geometry is continuous, but the behavior of light? It gets completely wild. At the exact moment you cross, the light from the horizon appears as a line that suddenly splits, expanding into this enveloping white bubble. It's this incredible optical illusion where the event horizon you just passed through seems to completely swallow you up, locking you inside a pocket of completely warped space-time.
Let's see how this builds to the inevitable and kinda terrifying conclusion. Once you're inside that bubble, space-time itself is literally flowing inward at the cosmic speed limit, the speed of light. You were dragged 79,500 miles toward the one-dimensional singularity at the center, and because the gravitational pull is so much stronger on your feet than on your head, you get violently stretched out like a piece of string. Astrophysicists actually literally call this process spaghettification. From the moment you cross the horizon, your total destruction takes a mere 12.8 seconds.
Section 6. The slingshot survival scenario. Now, since being spaghettified in under 13 seconds isn't exactly anyone's idea of a good time, let's look at an alternative scenario. Say you fly your spacecraft right up to the edge, skim the event horizon, and safely slingshot back out into space. For you, this insane joyride takes exactly 6 hours. But when you get back to your mothership, you're going to find that you are 36 minutes younger than your crewmates who stayed behind. Because time actually passes more slowly near a massive gravitational source, and because you're moving at near light speeds, you literally experience time dilation. Oh, and if this black hole were rapidly rotating, you could potentially return many years younger than your friends. Talk about a crazy fountain of youth. So the real crucial takeaway here is that a black hole doesn't just devour matter. It bends both light and time in unimaginable, almost hallucinatory ways. It transforms the universe into this funhouse mirror of photon rings and horizon bubbles. We've seen the sheer, mind-bending beauty of the accretion disk and the fatal reality of spaghettification. All of which leaves us with one final, provocative question. Knowing the physics, the massive risks, and the time-bending reality of the event horizon, would you take the plunge?